If you're new to Climate Action Tech, we are a community of tech professionals with the goal to inspire and empower each other to take climate action.
And we're super happy to be with you today. This is a rough timeline for the agenda that we propose. So, 10 minutes whereby we'll share with you, the purpose of CodeCarbon and what it is. And then what we want to do is to show you a demo of the tool. We might go longer than 10 minutes, but it's, we want to get right to the heart of the matter. And then, we'll be happy to engage on Q&A as Matt mentioned. So, the one critical thing to bear in mind regarding CodeCarbon is, this is the product of a partnership that was involving 4 organizations. So Mila, that Victor belongs to this organization, the research center based in Montreal, and working with Yoshua Benjo, who has released the tool on a press conference in December last year. So I think it's quite dear to his heart, to push that kind of initiatives. And then my organization, BCG Gamma, so we're 1,000 of data scientists and AI practitioners. The Harvard College with Jonathan today, and then several other people who contributed, as well as Comet.ml, which is an MLOps startup based out of New York City. So we came together and worked like in the evening to get this product out in an MVP fashion. We'll update you around the fact that it's a roadmap that we're engaged in, and it's a lot of fun working with these folks. So we'll also make a call for action at the end of the presentation, because the more the merrier, generally speaking. But just wanted to ground ourselves in this perspective. So without further ado, Jonathan, the floor is yours.
Thanks, Tristan. Thanks everybody for the invitation to come here. It's really wonderful to speak about this to this audience. And I think to this audience in particular, as everyone is aware, AI and ML tools are critically important for fighting climate change and reducing emissions in a variety of spheres worldwide. And there have been a number of publications on this over the last several years that have outlined that the possibilities are many, from improved responsiveness and precision of indoor and outdoor environments to using AI to help inform decisions on transportation infrastructure. However, the problem with this, or the challenge, is that AI and ML tools come at a cost. And one of the costs is the energy used to train the models and run the underlying analyses. And the source of this energy, whether it's from fossil fuels, comes with this environmental cost. And there's been a lot of energy paid to this lately, a lot of energy and attention paid to this lately, because this is a matter of some urgency. As you all know, that these tools and their deployments are growing significantly wider. We see it both in the private and the public sectors, and with the pace of this growth is outpacing the rate at which efficiency gains could make the powers cost neutral. So let me just highlight a couple of particular challenges of this that many of you might be familiar with. The fact that models are getting larger, requiring more computation and more energy for training. Tools are getting easier to use and also hence more widely deployed across the private and public sectors. And most of the hardware efficiencies that we've seen lately have been these one-time improvements, migrating to cloud providers or marginal hardware improvements. And this is actually a particularly thorny type of environmental problem, because the emissions of this work are actually opaque to the user. So how would you know if your emissions are growing out of control, or whether you've passed the efficiency computational efficiency, and then diminishing returns peak threshold? How would you know where you are if you don't understand this and if you can't measure this? And also, if you measure it and the numbers are growing out of control, how would you interpret that information? And these are the questions that actually motivated our collaboration, which is focused on really answering these questions. We know that many people are concerned about this issue. What the numbers that mean. And although there's been increasing transparency from cloud providers recently, there's a general lack of transparency in the energy industry overall. And as we see these tools becoming adopted more broadly, it's likely that you're going to see computation occur off the cloud or in other places. And particularly if it's occurring on the local energy grid, that can be heavily sourced by fossil fuel. So to address these issues, we focused on three objectives of the CodeCarbon project. And the first is to foster the visibility of the carbon footprint. So your hardware runs on electrons. Where do those electrons come from? And second, we wanted to devise a tool that is as simple as possible to use and whose results are easy to interpret. For example, I'm in an academic environment. Could we make a tool that our small college's IT department would be comfortable deploying to measure our footprint? And finally, the last part is that we really wanted to make this tool open source and widespread. We know that we're not alone in being concerned about this problem, and we wanted to make sure that the doors to our collaboration are open to everyone. So let me pass it to Victor to talk about how CodeCarbon actually works.
Thanks, Jonathan, for the introduction, and thank you everyone for having us here. It's really great to be able to share this tool. We've been working on this for quite some time now, so we're very happy that it's at a point right now where we can widely share it and trust that it's going to be deployed, or it can be deployed. And I'm going to get right now into a little more specifics about what it does. And the first goal that we had developing CodeCarbon was it should be easy to use, and so that's why it's just a pip installable package, which, as we'll see later, you can just you start it, it records, you stop it, and then you have an output, right? So the goal here is to be able to first measure the power consumption of the hardware that the Python script is leveraging, and then map that energy to carbon emissions depending on the location of the user. As we can discuss, I'm sure in the Q&A, we'll see that there's a few assumptions there, and there are simplifications that are made. Some of that comes from the infrastructure in which the code is run, and this comes back to the call that Jonathan mentioned for more transparency from cloud providers. So now that we have measured, or that we have an approximation of those emissions, then a very important step is that these measurements are understandable and leverageable. So this is why there's a dashboard included that will present information in an interactive way. Also, to present information that is beyond just numbers, there are things you can do. And for example, one of the things that we do recommend is that if you can, then and if you're using, for example, cloud infrastructure, then taking into account the amount of electricity that is used and the type of energy of those cloud infrastructures is going to matter a lot for the final emissions. And the tool helps you do that by comparing cloud regions. And then, of course, as Jonathan mentioned, this is all open on GitHub. The code is there. There's no licensing or anything, and it is driven by the community, which for open source contributors, you all know it's a nice word. It means there's a few people who work a lot and who help manage the issues, and we all know it's not such a beautiful world, but what matters is that it is under active development, and the community is growing, and that's really a very good feeling. So I won't get into the exact specifics of each of those boxes here. What matters is overall, the tracker is a Python object that you can start, that will start a thread in the background, and you can have your training loop or your computations there. Whatever happens, that's up to you. It is irrelevant to the tracker, and then the tracker stops. And what happens in between the start and stop loops calls is the tracker is going to try and measure every 15 seconds. So that's a parameter you can set, but it's going to try and measure the energy consumed by the hardware that it can see. The hardware that it can see is either a GPU or a CPU or more than one of those. Tracking GPUs is actually quite easy if you're using NVIDIA GPUs, thanks to the interface that NVIDIA provides, but tracking CPUs is very challenging. There are hundreds of CPUs out there which have very different interfaces and which are sometimes not available at all to the software, for example, in virtual environments such as Docker or cloud machines. Then you don't have access to actual hardware, you have access to parts of some hardware. And so some of those bindings are broken. And in that case, we have this constant mode fallback where we assume that, well, you're using this CPU, this kind of CPU, we know that they have a consumption, a TDP of that much, and we're going to rely on that. It's imperfect, but it's better than nothing. And then at the end, when the tracker stops, it writes the sum of all the energy that has been measured during the between the start and stop calls, and it writes the data to a CSV file on your file system. And that will be all for the details of how it works inside in the Python package. Tristan is going to continue on use cases.
Yes, exactly. And this is a very simple way of showing a few examples where you really have to think about consciously your carbon footprint when you run AI experiments. And by the way, we've spoken a lot about AI, but frankly, it can be employed in any, Python glued kind of code, computing, which can be whatever, So it's not just AI. That's important to note. But of course, like if you employ this lens, there are a number of situations where it's a no-brainer to be willing to track the CO2 emissions. So for instance, when you retrain your model every hour or even every day on a very frequent basis, it's going to be important to manage the run CO2 emissions. You have huge models or a lot of data which get processed either in the initial training or in the ongoing retraining, or even if you're streaming live data in industrial settings, in web-based applications and the like, it's obviously driving emissions up. The sophistication of the training algorithm as well. Jonathan hinted at this earlier on, but some algos are getting extremely sophisticated these days, like to grab a couple points of accuracy and sometimes less than that. Use of serialized GPUs as well. And frankly, if you live in some places which are not Norway, Quebec, or France, just to name a few, if you live in certain states in the US, if you live in certain European states or in Asia, in many places, and so on, then every kilowatt hour is loaded with CO2. So it's pretty obvious, but that's an important aspect as well. So it's the code, it's the data, it's your location, it's a set of factors, and it's also the way you use your models. Are they in production or are they on the workbench and so on? So if you think about it, apart from tiny models or POCs or trials, I mean, the case for using this is pretty wide. Now, we don't ask you to trust us just with slides. What we would like to do is to show you how it works. So we'll move to a demo. And it's actually going to be a recorded video, so bear with us. We've seen all, I think, examples of live code demos that crash. It doesn't crash, but we wanted to remove that 0.1% chance of that happening. So it's going to be a video, and we'll reiterate on those messages, but the key things we would like you to remember from this is really like it's the simplicity of using CodeCarbon, which was a fundamental design factor in every decision we made along the way. It's not just information for the sake of information. People should and can do think something about their emissions, so it's really actionable, and that's the goal. And I don't want to get too philosophical, but bear with me just a minute. It's on the individuals to push that improvement related to emissions of CO2 related to computing and AI. It's also on the part of organizations. And there is a lot in the tech world which is not transparent, in particular around this kind of subjects like CO2 emissions. So we really want to empower individuals, but also organizations to track their CO2 emissions. So those are the principles that led to the build of CodeCarbon. So now I'm going to share the video, and hopefully it's going to work seamlessly. So let me click there. Whoops. Hold on. All right. Stop me if it doesn't work. It works well?
It has started.
Everybody,
yes.
Yeah? Okay.
All right. You're
perfect.
All right. So
go ahead.
Let's start with the website. That's CodeCarbon.io. You have a lot of information there, but it's mostly a presentation website. It's the goal here is to gather information such as a Medium article, the motivation about this package, and so on. And really, what matters are the links that are there, the link to the GitHub page and the documentation. So that's the GitHub webpage for CodeCarbon. That's where our code is stored, and that's where we basically have most of the instructions and the context. It's super easy to install. You just pip install, and usually that works. If it doesn't, it's probably more on you. But that's how we designed this thing. It should be super easily installable. Right. So here's a new environment. We have just installed CodeCarbon, a few dependencies to be able to run the code, and the goal here is to show you how it works with a dummy experiment, like training a model to predict handwritten digits on the MNIST dataset using Keras. So that's basically it's a super simple model because, well, the goal here is not to delve into the AI, but what's going to matter here is that in the training loop, there's the emission tracker that is imported at the top from CodeCarbon import emissions tracker, and then in the main function, we're just going to define everything we need, start the tracker, give it a project name, whatever, that's up to you. And then we just start, run a grid search, and then stop. And then we're going to be able to see on the CSV and the output CSV file the result of those emissions. So here we have the grid search I mentioned. So this means we're going to test various parameters, and we're going to try and see which are the best parameters to perform handwritten digit recognition. So here are a few epochs through the data. Our super fancy algorithm learns everything, and we're going to try a few parameters. Beyond just grid search, there are other ways to look for hyperparameters. There are actually many ways. One of the other ways that we can use to look for parameters are random searches. So here, instead of iterating through a list of values that we think are going to be good parameters for the model, we're going to randomly sample them. And just like before, we start the tracker, we give it a different project name, we run our random search, and we stop the tracker, and that's going to output another line in the CSV file. So by default, it's going to write to the same CSV file. It's just going to have a different project name so that later we can aggregate those results. That's very important to remember, and that's one of the core goals of CodeCarbon, is to be able to not just run one experiment and have one number, but also to be able to aggregate the results over several experiments, several projects, and showcase the data. So here is well, the output of the random search. We can see, I'm not sure you can see, but you could have seen the values compared. What matters is that you'll see in the CSV file and in the live demo, not in the live demo, in the data viz, how those values compare.
Yeah, and then when you dive into here, if you look into the emissions.csv file, this saves all the results of your experiments, and in it, it's it's just a raw file that can be processed. It saves the value of emissions in kilograms, kilograms of CO2, the duration of computing time, the energy consumed, and the location of the computing that's there, and it stores this entire history in this historical CSV file. And then you can take this, and if you copy and paste this code, you make a slight little modification of this. This will actually call up the visualization of this. And this is where it takes the emissions values that have been recorded and puts them into context. So you can click on this and it pops up, and here you go. And this gives you the outputs of your projects at 3 levels across all of your projects, for one specific project, and for the last experiment that you've done. And the outputs that are displayed here are the power that's consumed. You can see there the power consumption is 113 kilowatt hours, and equivalent CO2 emissions. And you can see here it's 120 kilograms. So across the work, you can see that it's a significant amount of kilowatt hours of power, representing roughly 527 kilograms of CO2 equivalent. And it talks a little bit about what the last run is. And to give you some examples of this, this gives you some context of what percentage of the average American household this is used, and miles that are driven by a car or a TV, to give you the kind of sense of global context of what these actually means. And when you look through these benchmarks here, you can look through and it'll tell you what the emissions equivalent is and what the possibilities would be if you ran your computations in different countries. So it gives you not just the local context of what's actually happened with your computation, but actually what is the local energy, what does the global energy grid look like, and how do your results compare with what is being done around the globe. And if you take a look down here, it shows you the trend of your CO2 emissions over time. So some days, it's all close to, 8 to 10 kilograms of CO2. On other days, it's relatively low. So that helps you track your impact over time and what the sort of trend of your emissions are. And this is a project here where, looking at this, you can actually look at a project that is running on the AWS cloud. And this gives you the carbon emissions that would have occurred depending on which data center you run your project in. And if you can, it's best to select a region that's greener here on the left. And that all depends on the electrical power source for each data center. So you can see the data centers that are the greenest there on the left. So if you chose to run it in there, you'd be close to 1 or 2 kilograms versus the data centers on the right. And let me turn to Tristan for a concrete example here.
You must be muted, Tristan.
Yes, I was muted. Thank you. What we've done is we've taken the experiment that you shared, Victor, the grid search and then the random search in 4 different countries: Germany, USA, Canada, and France. This graph here is showing you the amount of CO2 emissions in milligrams of CO2. So first of all, there are a few key takeaways that you can derive from here. There is an obvious and massive difference between grid search and random search. And random is actually much more efficient in terms of computation. And you might have noticed, I don't know if you saw on the screen, but actually the accuracy of the model was even better. So it's not a trade-off between accuracy and power. I mean, not always. There is oops, the video is going too fast for me today. There is another key learning from this is that, in both scenarios, grid search and random search, depending on the energy grid that you're considering, there is another important factor of reduction potential that comes from the location where the computing is done. So those are, two important levers that are at our disposal. And so now, if we just have a kind of a look at the from to, if you do a computing intensive process in Germany, you get to the large light green bar to the left. Now, if you actually move from grid to random, you can cut your power consumption by 80%, even a bit more. And then if you take advantage of a greener energy mix, then you can reduce it further by 60%. And this is a sample, it's not an absolute truth, but if you compound both effects, you get to a reduction of over 90%. And the learning here is not this number. The learning, I would say, is rather the magnitude of what that represents. The potential for improvement is really massive. And it's really like a good example to show that we're not talking about 2 to 5% reduction. We're talking about an order of magnitude simply. So that can make a big difference, especially for the types of use cases that I highlighted before. So I'm not going to play the end of the video because we're going to cover it in better with the slides. So Victor, if you can pick it up again, that would be perfect.
All right, so you should be able to see that, right?
Yeah, perfect.
Cool. Okay, so the next part is basically our conclusion, and in 2 steps. And the first one is going to be describing what we're currently working on and what are next steps, and if you want to, how you can help, or if you know people who might be interested in that kind of work. Here are the 3 big directions that we're working towards right now. So the first one, which is more software engineering with respect to the package and data collection, is how can we handle more hardware configurations. That means better handle Dockerized or containers environments, better handle cloud environments. For now, we don't have AMD support for the CPUs, for instance, which is something we're working towards, and so on. So what matters is being able to interface the package with all those possible hardwares. And when that's not possible, come up with heuristics so that we have approximations instead of actual measurements, but is you might not want to always store everything in a CSV file on your file system. We know that can have limitations, especially for larger organizations which have teams and so on. And the vision here is that hopefully we can design a tool and an API that will collect the data either online with a hosted service, or locally with some like the code that you have deployed yourself in your organization. But the goal really here is that in a couple of clicks, you can have the entire emissions of your whole organization for all the teams and all the projects over the past year, for instance. That's really the vision. Of course, it requires engineering, and that's where we're at right now. And lastly, there is work, but it's actually more conceptual right now. We haven't started improving the Dash app that you just saw, but the goal here is to move the front end from a Dash Python app to a more modern REST structure, so that also we can better handle community dashboards and so on. So here the challenges are more web-like, so UI, UX, and any front-end framework is welcome. So I'm basically trying to organize this community, and we're working currently with an NGO based in France, which is called Data for Good, and they have volunteers work on projects, and we're part of the 9th season they are having right now. So there's actually a big push right now. So everyone's welcome to join. It's never too late, and the more generally, the things you can do if you think this is a cool project and you care about that is, well, you can use it, give us feedback. You can use either my email or the GitHub issues online. You can obviously share this project around you, especially if you work in a compute-intensive organization and you'd like to see this tool deployed. I think I'm going to talk on behalf of Tristan here, but I think he can have very, very important insights on how he did it in his organization and how you could probably do it if you wanted to do that. And yeah, obviously share your feedback, your suggestions, and you can either through an issue or email, you can also reach out and say, hey, I have a couple of hours to spend and I want to help.
And I will just add one thing, Victor, you're absolutely right. In BCG Gamma, we're right now working hard to embed this into our project because it's really important for us and for our clients as well. Given it's completely, open source, free, etc., one can take it and reshape it to fit an internal organization. I think, we've seen a lot of companies, but also not-for-profit organizations, think about how can they move their technology to a green technology landscape, or at least greenify it. And that involves a huge amount of effort and strategic thinking and implementation. But CodeCarbon is an excellent proof point that it's doable and that it yields outcomes. So it's not the solution to everything, but it's a really crisp way to convince some reluctant IT people, for instance. So a good idea to try it out, and it's actually a lot of fun working on this tool. I'm just saying.